Thank you for coming today. It's a delight to be with you. I wish I could be with you in person. Today I'd like to talk about replication and evidence factors in observational studies, and I'll say what I mean by that in a moment. There is a handout for the talk. You can get it from the JSM webpage or from my homepage. It has the notation, it has some of the key ideas, it has some R code so you can try the calculations that I'll be describing, and it has the references. If you get it from my personal web page, it looks like this, and the fourth button down in the center of the page would give you the one-page handout. This is a talk in 4 parts. The first part is about replicating effects and biases. It's mostly conceptual, it's fairly brief, it's neither original to me nor is it widely believed. So although it's advocated by quite a number of people, it's not really opposed by an articulate point of view. It's opposed by a preference to imagine the world a different way and think about other things. So this first part will have a number of quotes emphasizing the fact that the ideas are really those of other people. We're going to find that because biases can replicate in observational studies, replication should not be repetition. The second part, a central part of the talk, is about evidence factors. So there'll be an example and some theory. I'm going to hang the theory on the example. This second part is slightly technical. It's not very technical, and it's a little longer. It asks the question, can an observational study replicate itself? Can there be 2 independent analyses of the same data that combine to be stronger evidence of cause and effect than either is on its own? My goal is to bring into formal statistics an important aspect of causal inference that's currently informal. It's often decisive in the way people actually reach causal conclusions, but it isn't part of the analytical framework we have, and I'd like to bring it into formal statistical reasoning. The third part will be another example. It's an example where it's not obvious at first, very simple example, but it's not obvious at first that the theory we were doing in part 2 covers this as well. But after a moment of thinking about it, we'll realize that it covers this situation also. And as time permits, I will talk about constructing matched designs with evidence factors. This is joint work with Bikram Karmarkar and Dylan Small, and it's about the algorithmic aspects of design. I want to begin with 2 facts and a question about them. So these are completely uncontroversial facts. The first fact is that association does not imply causation. The treatment a person receives and the outcome the person exhibits may be associated in the absence of an effect caused by the treatment. In statistical terms, in the absence of randomized treatment assignment, causal effects are not identified by observed associations. The same observable distributions that give rise to observed associations are compatible with a causal effect or with biased treatment assignment or with both in some degree. The second fact is that smoking causes lung cancer, and we know this. In fact, we know this as well as we know anything. There's nothing defective in our knowledge that smoking causes lung cancer. And yet, despite the fact that there's nothing defective in our knowledge of smoking causes lung cancer, we know this fact on the basis of the very sort of associations in non-randomized observational studies that do not identify causal effects. So the question is, how can fact 1 and fact 2 both be true? They sound contradictory. Let's start with a claimed replication of 3 observational studies. So in the 1980s and 1990s, several studies were conducted of the effects of clinical treatments for addiction to heroin or cocaine. So in the earlier part of this period, it was mostly heroin, and in the later part of the period, it was both heroin and cocaine. Does clinical treatment help people to reduce their addictions? So one of the studies involved the DARP system, another the TOP system, and another the DATO system, big data collection systems for clinical treatment for addiction. These studies are sometimes cited as replicated evidence of treatment effectiveness. For example, Hubbard et al. Wrote, the general finding from DARPs and TOPS that treatment duration of at least 3 months is associated with statistically and clinically more positive outcomes supports the inference of treatment effectiveness. The following analysis retests this hypothesis using Datos and reaches the same conclusion. What should we make of the fact that a similar association was seen 3 times in large observational studies? In 1999 and 2001, the National Academy of Sciences published 2 reports that did a variety of things, but among other things assessed whether these conclusions about treatment effectiveness were warranted on the basis of the evidence provided by these studies. So I do want to emphasize the question that's being asked is whether the conclusion is warranted on the basis of the evidence, not whether the evidence from a variety of other sources is decisive. Concerning treatment effects, Mansky wrote, so Mansky was the chair of the committee, and the et al. Includes the rest of the committee and also the members of the NAS staff who were involved. Collectively, they wrote, the RAND study compares the post-treatment average drug use of members of the TOP sample who completed their treatment programs with drug use of TOP subjects who began treatment but dropped out within 3 months. Suppose, however, that treatment dropouts are more predisposed to drug use than are those who complete treatment. If dropouts are more severely addicted or less motivated or have fewer social supports than those who complete treatment, the observed differences in post-treatment drug use of dropouts and completers may reflect differences in the characteristics of the groups, not the effect of treatment programs. They continued, the people who complete their treatment program may be those who are most likely to reduce their drug use whether or not they receive treatment. The true post-treatment effect may be smaller than estimated by RAND, or even 0. So this is the claim we began with, right? The claim that the comparison is ambiguous. In this case, the most likely effect of clinical treatment for addiction, that it reduces addiction, predicts the same association as the most likely bias, namely that people who stay in treatment programs are most determined to end their addictions, and people who drop out are least determined to end their addictions. So we expect the same association from a treatment effect and from the most plausible bias. In statistical language, once again, the situation is not identified by the observed associations. 2 very different conclusions about treatment effects, causal effects, are compatible with the same data. And the problem is not having more data. These were large studies. Having larger studies wouldn't have done it, and having more studies, more than 3, wouldn't have done much either. Finding the same association 3 times is of very limited value if the main ambiguity keeps recurring in all of these 3 studies. So I'm going to turn now and quote from various people about this subject. 1 statistician, 1 epidemiologist, 1 mathematician, and 2 philosophers. So the statistician was William Cochrane, who got us talking about observational studies as a subject defined by principles and methods of statistics. He wrote, the combined evidence on a question that has to be decided mainly from observational studies will usually consist of a heterogeneous collection of results of varying quality, each bearing on some consequence of the causal hypothesis. The investigator cannot avoid an attempt to weigh the evidence for and against, since some results are so vulnerable to bias that they should be given low weight, even if supported by routine tests of significance. So I want to call attention to a couple of aspects of this. He's talking about a heterogeneous collection of results of varying quality, each bearing on some consequence of the causal hypothesis, which may have a lot of consequences. He's cautioning us that we shouldn't pay too much attention to routine tests of significance which say adjusted for a few things, and I still saw the association, because some of those results are so vulnerable to bias that they should be given low weight, even though the p-value happens to be small, under the unreasonable assumption that your adjustments have removed all the bias. The epidemiologist was Mervyn Susser. He wrote, the epidemiologist seeks consistency of results in a variety of repeated tests. Consistency is present if the result is not dislodged in the face of diversity in times, places, circumstances, and people, as well as of research design. The strength of this argument rests on the fact that diverse approaches produce similar results. So once again, he's emphasizing the importance of variety in the evidence, that things have been varied and yet the same conclusion about treatment effects keeps reappearing. The mathematician was George Polya. He obviously wasn't writing about observational studies, he was writing about heuristics in mathematics. So heuristics in mathematics is the process of reasoning that we go through before we have a proof. It's the process which helps us decide what's worth proving. It's the process that helps us construct a proof. It's the process which helps us decide that maybe we should stop working on a proof and work on a counterexample instead. It's the process which helps us decide that our efforts to find a counterexample are leading nowhere, and maybe we've discovered something in that and go back to constructing a proof once more. Mathematics is interesting because there's no sampling variability. There's often a lot of uncertainty about whether a mathematical conjecture is true or false, and yet it's not sampling uncertainty. Polya's argument is an explicitly Bayesian argument of a qualitative nature. So it's a Bayesian argument, but the numbers have been left out. And he's saying if you put in numbers here and there which are related in a certain way, what would come out of the Bayesian machinery are numbers which are related in a particular way. So that's the kind of reasoning he's describing. He says our confidence in a theorem can only increase as a new consequence of the theorem is established. The increase in our confidence brought about by a new confirmation, or if we wish, the inductive evidence furnished by this new confirmation, will vary inversely as the plausibility of the new consequence appraised in light of the previously verified consequences. The consequence which, on the basis of preceding verification, stands the best chance of refuting the given theorem will disclose the strongest inductive support if it is confirmed in spite of forebodings. This will be the case when this new consequence has no immediate relation with the old one, when it is removed from the preceding, when this new consequence is not only new, but of a new kind. So this is a sharper statement than the two previous quotes we're making, because he's actually talking about what particular types of variety of evidence would be most useful to us. It's the kind of variety of evidence that keeps placing the theorem at significant risk of being refuted by a new consequence. So let's go back to our original question. How does an empirical association demonstrate a causal effect if that association is compatible with both an effect and a bias? How do you prove you're looking at an association that's a causal effect and that's not a bias? Our first philosopher is Wittgenstein, and he said, a picture held us captive, and we could not get outside of it, for it lay in our language, and language seemed to repeat it to us inexorably. So what's the picture here? The picture is that observed associations demonstrate conclusions, as in a deduction or a proof. But what if that's not how evidence of cause and effect accumulates? What if it's not actually the case that the moment a paper appears in the New England Journal, it has demonstrated certain conclusions about cause and effect? How do philosophers break free from a picture? They do this by offering alternative pictures. The alternative pictures are not intended as substitutes for the original picture. They're intended to make it clear that the original picture is not the only way of looking at something, and that there are alternatives than the picture that's holding us captive. The philosopher of logic, Susan Hauck, suggested a different picture in her book, Evidence and Inquiry. And it's the picture of a crossword puzzle. So I'm going to describe Hauck's conclusions in our language. She uses some of our words, like independent, but uses them in ways that don't have anything to do with the way we use them. So rather than translate, I'm simply going to use our language to describe her conclusions. Her first point is that the clues in a crossword puzzle do not identify the entries that you need to fill in. So, for example, 16 across is German wheels in 4 letters. And that turns out to be an Audi, but it could have just as easily been an Opel. So an Opel and an Audi are 2 German car makes. They both have 4 letters. They both fit the clue. They both fit in the space. And you could not tell which it is simply from the clue. No amount of staring at 16 across is German wheels is going to settle the matter. 1 across is Desert Storm missile in 4 letters. What is it? Well, we might guess Scud, but we might be wrong about that, just as we would have been wrong about 16 across if we'd guessed Opal. One down is cry noisily in 3 letters, maybe beginning with S. 4 down is hound. We don't yet know whether it's the animal or the activity, in 3 letters, perhaps beginning with D. So we might guess sob and dog. 17 across is an optimistic viewpoint to look upon in 10 letters. We might guess bright side. So her second point is that a lot of the reason we have for believing we filled in a crossword puzzle correctly is the coherence of the entries we've created rather than the direct support provided by the clues. The clues were important, but they're only part of the overall picture. Sob is supporting Scud. Dog is supporting Scud. Those are other pieces of information than we started with from the clue. Her next point is that coherence lacks sharp boundaries. So in particular, bright side does not intersect with Scud, but it provides quite a bit of support for Scud because it intersects with sob and with dog and sob provide direct support for Scud. So as we're filling in this crossword puzzle, entries that are quite remote from the issue at hand are actually providing support because they're providing support for things which provide support for things which provide support, direct support for a particular entry. Coherence lacks sharp boundaries. This reasoning is circular, but it's not viciously circular. So viciously circular reasoning is an error in logic. If I say A implies B, B implies A, therefore A and B are both true, I've committed an error in logic, vicious circularity. A and B could both be false, even though both implications could be true. It's not viciously circular because we have evidence for the entries besides their appropriate intersections. So another point that Hauck makes is that our evidence may be demarcated. We can ask, what evidence do we have for Scud apart from the fact that it intersects appropriately with sob? We can ask, what evidence do we have for sob apart from the fact that it intersects appropriately with Scud? If the only evidence we had for sob and Scud was their appropriate intersection, we'd have almost no evidence, and coherence would be of almost no value. So we can ask, what do we have in the way of evidence for Scud apart from its intersection with sob? Well, we have the clue is compatible with Scud. We have its appropriate intersection with dog. We have the appropriate intersection of dog with bright side. What evidence do we have for sob apart from its appropriate intersection with Scud? Well, we have the evidence provided by the clue. The intersection of sob with bright side is also providing support, and the intersection of dog with bright side is providing support for sob that's of an indirect nature. So we actually have a lot of evidence for Scud apart from the evidence provided by sob. And we have a lot of evidence for sob apart from the evidence provided by Scud. And when they meet appropriately, that's providing us with a lot more evidence because both of these well-supported things are cohering. And had they met inappropriately, it would have provided us with a lot of reason to be concerned. Right? So the reasoning, again, is circular, but not viciously so. We can demarcate the evidence and break it into pieces. The peculiar thing about crossword puzzles is the lack of identification is never gone, but it keeps diminishing. As we fill in more and more of the crossword puzzle, there's less and less concern with lack of identification, even though logically it hasn't gone away. It's at least conceivable that somebody could create 2 ways to fill in the crossword puzzle, compatible with the clues, intersecting appropriately, and yet be incompatible with each other. But in any actual crossword puzzle, that possibility seems remote by the time we're done filling it in, even though at the moment we filled in Opal for 16 across, it was perfectly plausible that that was a mistake. One last word from the philosophers. Wittgenstein said, light dawns gradually over the whole. And that's a description of filling in a crossword puzzle, and it's not the description of proving a theorem. Here's a two-slide example of observational studies containing replications that are not repetitions. So in the 1950s and 1960s, many studies had found strong associations between smoking and lung cancer. People who smoked a lot tended to get lung cancer. That's one piece of evidence, one entry in the crossword puzzle, if you like. They also found weaker associations of smoking and cardiovascular disease, which today we think are causal, and associations between smoking and cirrhosis of the liver, which we today believe to be spurious consequences of greater drinking on the part of smokers. What would be another intersecting entry? Well, in the 1960s, the tobacco industry decided that women weren't smoking enough. It was frowned upon for women to smoke in the 1950s or so. And they wanted to change that, and they played on the women's liberation movement, which was very active in the 60s. This was most famous in the Virginia Slims advertising campaign with the slogan, "You've come a long way, baby," which was launched in 1967. So this was a campaign that showed attractive, slender young women, glamorous women, smoking. Smoking is an appetite suppressant, so there is a certain consistency with being slender and smoking. And they were smoking in defiance of convention, and they were smoking in defiance of men, and they were smoking in defiance of the advice of public health officials. In 1997, about 30 years later, about the right amount of time for lung cancer, Baylor and Gornick wrote, "For lung cancer, death rates for women 55 and older increased by almost 4 times the 1970 rate. But the rates for males over 55 and rates for other cancer sites show no such dramatic change." So this is a very different kind of piece of information than we had in the epidemiological studies, because here we see a group of people who were induced to smoke by an advertising campaign, and following their increase in smoking, for which we feel we know why they increased the smoking in response to the advertising campaign, we're seeing an increase in lung cancer. The second piece of evidence is just as fallible as the first piece of evidence, but it seems like it's fallible in a very different way. What could go wrong with the second piece of evidence? Well, at the same time that women were smoking more, they were also taking up jobs, often jobs that had previously been done by men, some of which exposed them to toxins in the workplace. And it's conceivable that it was something else in the change in behavior of women, not the increased smoking, that was producing the increased lung cancer. But that possibility seems to have nothing to do with the possible biases in the studies in the 1950s and 60s that found strong associations between smoking and lung cancer among people who hadn't been particularly changed in their behavior. Is there another intersecting entry? Most smokers don't die of lung cancer. It's nothing like flicking a light switch and seeing the light go on. Is there anything that is like flicking a light switch and seeing the light go on? Auerbach et al. Examined the lung pathology at autopsy for 4 groups of people, smokers and non-smokers, who had died of lung cancer and of other things. So we're seeing all combinations. They wrote, "From the standpoint of carcinogenesis, what impressed us most about was the tremendous increase in the number of atypical cells with the increased amount of smoking. The number of sections of atypical cells in the bronchial epithelium of heavy smokers who died of diseases other than lung cancer approximated the number of sections of atypical cells in the remaining bronchial epithelium of men who died of lung cancer. In our opinion, the histologic evidence from this study greatly strengthens the already overwhelming body of epidemiologic evidence that cigarette smoking is a major factor in the causation of bronchogenic carcinoma." So what are they saying? They're saying that when you look at an older heavy smoker who was run over by a truck, that person is very unlikely to have healthy lungs. That person's lungs are going to look a lot like the lungs of a heavy smoker who died of lung cancer. And in both cases, you're going to find a large number of precancerous lesions in their lungs. So this is like the light switch. It's almost always present, whether or not the person actually dies of lung cancer. This is another association that is fallible, right? But it's fallible in yet a new and different way, right? It's possible we really don't know what a precancerous lesion looks like, or people who have precancerous lesions for other reasons that are promoting smoking is a possibility. But it is fallible in a very different way than the two previous comparisons, and yet its conclusion is intersecting in an appropriate way, as in a crossword puzzle. So what have I been saying? Replication is not repetition. You don't fill in the same crossword puzzle entry 3 times and think that you've made some progress. If you can't eliminate a bias, what you want to do is to change it, right? You want to see if the same treatment effect seems to persist in circumstances which seem to be affected by very different biases. This raises a key question. If replication is not about doing the study twice, if it's not about increasing the sample size, then ask, can an observational study replicate itself? Can one observational study conduct 2 inconclusive analyses subject to different biases in such a way that the evidence against bias and in favor of a causal effect becomes measurably, quantitatively stronger? So we're into part 2. Evidence factors. There's going to be a basic example and some theory. The example is about smoking and periodontal disease. So a number of people claim that smoking does cause periodontal disease as well as lung cancer. Tomar and asthma claim this. The Centers for Disease Control claim this. We'll look at data from the 2011-2012 NHANES survey, which measured people's teeth very carefully, in particular periodontal disease, the separation of gums and teeth. The outcome we're going to look at is a measure of periodontal disease. So we're going to look at 28 teeth. That's what they looked at, excluding wisdom teeth. And they looked at 6 locations on each tooth, so 28 times 6 locations. And they judged a location to be diseased if there was either a loss of attachment of at least 4 millimeters or a pocket depth of at least 4 millimeters, 2 measures of the ways gums and teeth may separate. And the outcome is the percent of these 28 times 6 measurements that are diseased. It's the fraction of diseased locations. We have one of these numbers for each person. It's 0 to 100%. We're going to look at 441 matched pairs of a daily smoker and a never smoker. Smokers smoked every day for the past 30 days, whereas never smokers smoked fewer than 100 cigarettes in their lives. Daily smokers began smoking 30 years ago on average, and 90% have been smoking for more than 14.9 years. Pairs were matched for age, gender, 5 categories of education, income, and black race, but there's lots of other ways people can differ besides those characteristics. And we're also going to take note of the number of cigarettes smoked by the smoker in each pair. So we have 2 factors we're going to consider, but before we can consider them, we need to understand them separately. So I'm going to claim that there's 2 pieces of evidence, and they're going to merge to produce stronger evidence. But before we can get to the question of merging the evidence, we need to consider the 2 pieces of evidence separately and have a clear idea about them. Then we'll think about their combination. So the first piece of evidence is here in this box plot. It's the smoker minus control pair differences in periodontal disease, whereas the outcome for a person is between 0 and 100%. The outcome for a pair, the difference is between minus 100% and 100%. The box plot is showing you what? Here's the center line at 0. It's showing you that, in fact, most of the differences are positive. Smokers tend to have more periodontal disease than non-smokers, although there are quite a few pairs where the difference was negative. If we apply Wilcoxon's signed rank test to this box plot to test whether it's symmetric about 0, we find a p-value which is below machine precision. I've quoted it as 1 in 10,000, but you can't actually calculate it. We don't know any idea how tiny it is. It's just very tiny. The Hodges-Lehmann estimate associated with the Wilcoxon statistic is 13.5%, and its confidence interval is 10% to 17%, an increase in diseased locations of that amount from smoking. So there's no real doubt that smoking is associated with periodontal disease. And the natural next question is, did smoking cause this association? Are these effects caused by smoking? Well, what else could it be? A person who smokes is manifesting a certain lack of concern for their health. They're manifesting a certain disregard for recommended health practices. Maybe a person who does this doesn't just do this in one way, maybe they do it in several ways. Maybe the smoker is less inclined to floss their teeth. Maybe the smoker is less inclined to go to the dentist. Maybe it's flossing your teeth that really matters for periodontal disease, and that this association is spurious. We could imagine a randomized experiment. We couldn't conduct it, but we could imagine it, in which we flip a fair coin 441 times to assign one person in each pair to smoker or control. There would then be 2 to the 441 possible treatment assignments. We might list them, K1 through K2 to the 441, and each of these possible treatment assignments would have probability 1 over 2 to the 441 if in fact we had randomly assigned treatments. We could create a vector P, which is giving you the probability of each of our treatment assignments. If we compare smokers and controls using Wilcoxon's signed rank test, we got a p-value which was really 0 to machine precision and was certainly very small. Right? It's a randomization test. What is that saying? If in fact smoking did nothing to your teeth, it doesn't matter how I assign treatments, you're going to have the same amount of periodontal disease regardless. Then fewer than one assignment in 10,000, really much smaller than that, would accidentally produce Wilcoxon's statistic as large as the one we observed, and similar considerations apply to the confidence interval. It would be an absolute miracle in a randomized experiment if smoking didn't cause lung cancer and we'd randomized for you to see that box plot. That box plot would never happen in a randomized experiment if in fact smoking had no effect on periodontal disease. We're not entitled to that p-value because we didn't randomize. Cochrane's point, right? Small p-values can result from bias, not because of causal effects. So we're going to ask, how far from a randomized experiment would we have to be to explain what we saw? We're going to do that with a parameter gamma, which is going to talk about an imagined situation. We're going to imagine that we flipped biased coins independently, such that one person in the pair had at most gamma times the odds of smoking as the other person in the pair. So for instance, gamma equal to 1.25 means that one person might be 25% more likely to smoke than the other person. So the treatment assignment probabilities, the coins in those pairs, could range from 0.44 to 0.56 instead of all being 0.5. I'm not going to explain this in great detail here, but the gamma equal to 1.25 has an alternative interpretation. It is an unobserved covariate that doubles the odds of smoking and doubles the odds of a positive difference, pair difference in periodontal disease. So this is neither a trivially small bias, nor is it an enormous bias. It's something that's doubling the odds of smoking and doubling the odds of periodontal disease. It's a meaningful bias, but it's not an enormous one. This is going to create a set of distributions on our possible treatment assignments. Same possible treatment assignments, 2 to the 441 possible treatment assignments, but instead of just having that one randomization distribution where all the probabilities are the same, those 2 to the 441 possible treatment assignments are going to be assembled from individual treatment assignment probabilities in this interval into possible distributions on the treatment assignments. So where we once had a set consisting of a single randomization distribution, we now have a set of probability distributions, all of which exhibit a bias of at most gamma. We don't know the true p. If we knew the true p, and we knew it was in the set p gamma, right, we could just compute an appropriate Wilcoxon test, a p-value for Wilcoxon's test with that true value of the treatment assignment probabilities. Because we are only premising that p is somewhere in p gamma, the set p gamma, and don't know which one it is, we compute all of those p-values, and then we take the maximum one. And that maximum one is an upper bound on the p-value if in fact the bias is at most gamma. If Fisher's hypothesis of no effect were true, and if the bias were at most gamma, the biggest p-value you could possibly get is p bar gamma. If that guy is small, if it's less than alpha, then the chance that you would falsely reject the null hypothesis of no effect is at most alpha. So the premise is that the bias is at most gamma. What's the biggest p-value you can get? You get this p-value, and that's telling you whether a bias of that size could explain what we saw. At gamma equal to 1.25, the maximum possible p-value is above machine precision, but it's on the order of 10 to the minus 16th. Right? So a bias of that magnitude couldn't begin to produce the box plot we saw or the behavior Wilcoxon statistic. This unobserved covariate that doubles the odds of smoking and doubles the odds of a positive difference in periodontal disease couldn't even get started at explaining what we saw. At gamma equal to 2.75, the maximum p-value is 0.047, so it's just about to cross the 0.05 level. 2.76 would cross the 0.05 level. And that turns out to be an unobserved covariate that increases the odds of smoking 5-fold and increases the odds of a positive difference in periodontal disease 5-fold. So this is a hefty covariate. This is really something you should have noticed and found and recorded, and that's what it would take to change the qualitative impression that smoking is causing periodontal disease. Is that it for the data? Well, actually, there's a second comparison in the data. Let's consider the smoker minus control pair differences in periodontal disease in relationship to the amount smoked by the smoker. So you remember the pairs were matched for all kinds of stuff, right? So we're comparing two people who are similar, and we're looking at the difference in periodontal disease for two similar people. Do we see larger differences in periodontal disease in those pairs where the smoker smoked more cigarettes per day? So an alternative study design would have focused on how much people smoked and not whether they were smokers or not, whether they were zero versus positive smokers. So this is, and by the way, that's closer to what Asma and Tomar did in their paper. So these are the same pair differences in periodontal disease, minus 100% to 100%, but they've been plotted against the amount smoked by the smoker. And to aid the eye, the lowest curve has been added to the plot. Right? So what are we seeing? A smoker who, when the smoker smokes, 1 or 2 cigarettes per day, the pair difference looks a little positive, but it doesn't look very far from zero. Right? It looks like there isn't a big difference. But as the smoker is smoking more and more cigarettes per day, we're seeing this gradual rise in the typical difference in periodontal disease. This is that same picture. All the points are in exactly the same position. I've taken out the lowest curve, I've taken out the usual axes, and I've put in new axes. These new axes are defined at the 20 and 80th percentiles, so the quintiles. Up here you're seeing the biggest 20% of differences in smoker minus control differences in periodontal disease. Down here you're seeing the smallest ones, essentially the negative ones, where the control had more periodontal disease. To the right you're seeing the 20% of people, pairs, where the smoker smoked the most. They were at least a pack a day smokers. To the left, on this side, you're seeing the 20% where the smoker smoked very few cigarettes per day. Far less than 1 pack a day. The quantity that's being quoted over here is the cross-cut odds ratio. So that's the odds ratio which counts the 36 points in this cell, the 28 points in this cell, the 12 points in this cell, and the 23 points in this cell, and is taking the odds ratio. That quantity yields a randomization test, and the randomization p-value is 0.0022. So you would see this association fairly rarely in a randomized experiment. This cross-cut statistic turns out to be a very good statistic to use in sensitivity analyses. It has good design sensitivity. Again, that's not a topic I'm going to talk about in detail today. So We could imagine, again, a randomized experiment, a very different randomized experiment, that randomly assigned doses of smoking to the 441 pairs. We could do that in 441 factorial ways. A truly randomized experiment, which we can imagine but can't conduct, would assign all of those 441 factorial treatment assignments the same probability of occurring. Saying the same thing in different language, the odds of smoking D cigarettes per day rather than D prime cigarettes per day, that relative odds is the same for all pairs in a randomized experiment because it's assigned at random. Whether it's a pack a day versus 3 cigarettes per day, that relative odds is the same for all pairs because it's completely random. The quoted p-value says that about one randomization in 500 would produce a cross-cut statistic as large as the one we observed were the null hypothesis true in a randomized experiment. As before, we're not entitled to this p-value because doses were not randomly assigned. How sensitive is this comparison to biased assignment of doses? Suppose we quantify this in the following way. We say the odds of dose D rather than D prime of cigarettes varies from pair to pair, but it varies by at most a factor of gamma prime. One pair may have at most gamma prime times the odds of another of smoking D rather than D prime cigarettes. And randomization is gamma prime equal to 1. We now have not one distribution on the set of treatment assignments. We have a whole continuum of distributions on that set, all of them that are compatible with this constraint on what those probability distributions are. For each such distribution, we could compute a p-value for the crosscut statistic. We don't know which one to use, so we calculate the maximum p-value for all of those distributions in p prime gamma prime. If the bias in dose assignment is in fact at most gamma prime, then the chance that we will falsely reject the null hypothesis of no treatment effect at level alpha is at most alpha. So conventional p-values are acting like conventional p-values in the presence of a bias of at most gamma. And we're then going to vary gamma and ask how sensitive the conclusions are. The maximum possible p-value is 0.044 at about gamma prime equal to 1.6. Right? So it's at about that stage that we would start to regard the study as sensitive to unmeasured bias. If I switch to 1.7, the p-value would be above 0.05. So this is what we've been looking at. Two pieces of evidence. One is the box plot of pair differences to which we applied Wilcoxon's signed rank test, and the scatter plot of pair differences against amount smoked by the smoker and seeing whether they were associated. So we have two pieces of evidence. I want to convince you now that these two pieces of evidence are as if they came from two unrelated studies by different investigators working on different data sets. And in fact, you can do meta-analysis on these two analyses and put them together to produce stronger evidence than you're getting from either of the conclusions by itself. That's not completely obvious, right? Because after all, if you took the points in the scatter plot and you projected them to the left, and you removed the box and replaced it by the points here, the points in the box plot are simply the projections of these points to the left. So the box plot is completely dependent upon the scatter plot. So it's remarkable if these two things act as if they're from independent studies. Moreover, we imagine that the biases could be related. The person who's most likely to smoke may also be the person who's most likely to smoke a lot if they do smoke. So that needs to be in here too, and yet it seems that the claim, at least, is that these are like two pieces of independent evidence. So let's understand that. So my goal is to combine two sensitivity analyses. using the assumptions that are present in the two sensitivity analyses without adding any new assumptions at this stage. So I pointedly do not want to add the assumption that the biases in the first comparison are unrelated to the biases in the second. I do not want, under any circumstances, to add the assumption that being inclined to smoke and being inclined to smoke a lot are unrelated events. I want to let that happen in the worst possible way, compatible with the assumptions of the two separate sensitivity analyses. The basic claim is that the two upper bounds on the p-values can be combined as if they came from two unrelated studies. This claim rests on a couple of structural assumptions, one having to do with the nature of one of the test statistics and one having to do with the scatter plot and the box plot. But they apply it with lots of test statistics in lots of situations. It's not very particular to this use of two statistics in this particular context. This is the basic claim stated fairly informally. It says what? It says if the null hypothesis no treatment effect were true, if the bias in the smoker control treatment assignments was at most gamma, if the bias in the dose assignments was at most gamma prime, then the pair of upper bounds on p-values that we just computed is stochastically larger than the uniform distribution on the unit square. It's stochastically larger than two independent uniforms. And that's what we need to combine them as if they came from independent studies. So it's saying no matter how you built the joint distribution compatible with the assumptions of the two separate sensitivity analyses, you'd always get a bound that's stochastically larger than the uniform under the null hypothesis. So before I actually explain why that's true, let's just make sure we understand what's going on, what the analysis we're talking about is. So let's do the analysis and then we'll come back and check that it's actually an appropriate analysis. I haven't yet convinced you it's an appropriate analysis. Remember that Wilcoxon analysis became sensitive to bias at gamma equal to 2.75, and the cross-cut analysis of the dose relationship became sensitive at gamma prime equal to 1.6. So this table is letting both statistics have varying levels of bias in them and combining the results into a single analysis. So this is a meta-analysis of the two analyses we did. It's taking two p-values, acting as if they were independent, and it's coming up with a new p-value from them. The venerable way to do that is with Fisher's combination of p-values, where you multiply the two p-values and work out the distribution of the product of two uniform random variables. This table is using a different meta-analytic technique, one invented by Zakin et al., which takes the product of the small p-values, the p-values that are less than, in this case, 0.2, but there's a truncation point. That has a different distribution, of course, and we compare that product to its distribution and get a new p-value from it. If I truncated at 1, I would get Fisher's method, but this is throwing away the biggest p-values. That turns out to be a good thing to do in sensitivity analyses, because sensitivity analyses produce p-values that are much bigger than uniform under the null hypothesis, and so this truncating it is advantageous. So that's another thing I'm not going to explain in a great deal of detail. Why did I pick this meta-analytic technique rather than another? But this is a standard meta-analytic technique. So what would happen if we looked at the place where Wilcoxon was just about to become sensitive across 0.05 and crosscut was about to become sensitive at 0.05? We would get a new p-value by putting them together, and you notice the new p-value is much smaller than 0.05. In fact, we could increase both gamma and gamma prime. So if we increased gamma prime to 2 and we increased gamma to 2.9, we're still getting a combined p-value that's under 0.05. So the combined analysis is insensitive to larger biases than the individual analyses we're sensitive to. In particular, Wilcoxon's could be set at 3 and gamma prime at 1.8, and both values are larger than their individual cut points for sensitivity, but the combined analysis is insensitive to these larger values. So that's the first thing. The combined analysis is insensitive to larger biases than the individual analyses. Second thing is we can demarcate the evidence, as Hauk suggested. Right? We can set aside the evidence, say, provided by the crosscut test, say that's infinitely biased. Right? The bias there is complete, we can see that even if there were infinite biases, the combined analysis is insensitive to gamma equal to 2.5 in Wilcoxon's analysis. So there's a lot of evidence from Wilcoxon's analysis which doesn't involve the crosscut test. In the same way, if we look at this column 1.3 and at infinite biases affecting the Wilcoxon test, there's still quite a bit of evidence coming from the crosscut analysis, even if the Wilcoxon analysis in who smokes is infinitely biased by unmeasured quantities. So there's support for this conclusion from each factor. Each factor is contributing something. Neither factor is required for the conclusion, and their combination is considerably stronger than each component. So that's the analysis we're talking about. Let's now understand why it's appropriate. So I'm just going to make the study a little bit smaller. Instead of having 441 pairs, I'm going to have 2 pairs, just so we can think about it a little more clearly. The actual study is the same but larger. This is 4 treatment positions in an imagined experiment. So there's 2 pairs. The smoker in the first pair is going to smoke 40 cigarettes. The control is going to smoke 0. The smoker in the second pair is going to smoke 8 cigarettes. The control is going to smoke 0. We're going to permute people into these treatment positions. The actual study is just bigger. These are 4 people not yet assigned to a treatment position. They're in 2 pairs. The first pair consists of 2 men in their 50s. They're not black. They have some college, meaning something like an associate's degree, 2 years of college. And they have incomes that exceed 5 times the poverty level, the place where NHANES caps income reporting for confidentiality reasons. The second pair consists of 2 women. They're both in their 60s. They're both black with high school degrees, and they have incomes that are somewhat below the poverty level. The actual study is just larger, not different in concept. As we permute people into treatment positions, we want to keep the pairing intact. We've paired them very carefully. They're very similar inside the pairs. We like that. We don't want to break up the pairing when we permute people into treatment positions. A study design does what? It picks at random some way of assigning people to treatment positions. That would be the randomized experiment. It keeps the pairing intact. So how many ways can we do that? Well, there's 2 ways to assign doses to pairs, and then 2 ways to assign smoker control within each pair. So we don't have 24 or 4 factorial possible treatment assignments. We only have 2 by 2 squared treatment assignments, or 8 possible treatment assignments. These 8 treatment assignments are a subgroup of the symmetric group of the 24 4x4 permutation matrices. We could run a randomized experiment with this structure, giving probability 1/8 to each of those treatment assignments, and then we'd have a randomized experiment. Of course, that wasn't done. Without randomization, each of the 2 treatment assignments could be biased, and they could also be correlated. The actual study is just larger. So a treatment assignment is what? A treatment assignment is really a permutation matrix. So a permutation matrix is a matrix with 1, 1 in each row and column, and it rearranges people. In particular, if I took person 1, 2, 3, 4, and I hit them with this permutation matrix, I would rearrange them into 3, 4, 2, 1, which would mean the third person has been permuted to be the smoker of 40 cigarettes per day. And person 4 in the same pair is the control for that person. Person 2 is going to become the smoker of 8 cigarettes per day, and person 1 is the control for that person. So this is a permutation that respects the pairing and assigns people both a smoker control status and a dose of smoking. These are the periodontal disease outcomes for those 4 people. The first person had 63% periodontal disease measurements. The second had none. The third had 21%. The fourth had 10%. Fisher's hypothesis of no effect says what? It says if smoking doesn't affect periodontal disease, the first person is going to have 63% periodontal disease no matter where I permute them in this study design. If permuting them to different treatments changes what their level of periodontal disease, then treatment is having some effect on them. If smoking affects your teeth, it might change the level of periodontal disease, but if it doesn't, then moving you around the study design isn't going to do anything to you. That's what the null hypothesis says. Under the null hypothesis, we can save a lot of otherwise not needed notation by writing our test statistic as a function of the treatment assignment. We understand that everything about a person moves with the person, but nothing's changing about the person under the null hypothesis when they move from one corner of the experimental design to another. So if I zap 1, 2, 3, 4 with that permutation matrix, I would change the ordering of the outcomes to this, right? And under Fisher's hypothesis, the periodontal disease wouldn't change because the treatment has no effect. Of course, that's the hypothesis we're testing. We don't really necessarily believe that hypothesis. A group of 8 permutation matrices actually has a subgroup. This is the subgroup. So this is a subgroup which consists of 4 permutation matrices. And if you stare at it, you realize the first guy is just the identity matrix. The second guy is rearranging smoker control in the first pair. The third guy is rearranging smoker control in the second pair. And the fourth guy is rearranging smoker control in the both pairs at once. So there are 4 ways to change smoker control, and these permutation matrices do it. In the real problem, this subgroup is a bit larger, but it's not 4, it's 2 to the 441 elements. There's actually another subgroup, this subgroup, which is the identity matrix together with a permutation matrix, which is going to swap the 2 people among the 2 doses, the 2 pairs among the doses, without changing the smoker control status in each pair. So this is another subgroup of the group of 8 permutation matrices. In the real problem, this subgroup has 441 factorial elements, not 2 factorial elements. A curious fact is that 8 is equal to 2 times 4, right? So our group with 8 elements has the same size as 2 times 4, and we had a subgroup of size 2 and a subgroup of size 4. Actually, it's not just the sizes of these sets that are multiplying, it's the elements of the sets that are multiplying. So let's suppose we have 2 subsets of our 8 element group of permutations. So, or any set of any group of permutations. These 2 subsets may not be subgroups, right? But we're going to define a way to multiply the sets. And so ST is going to be understood to be look inside S, look inside T, take all the possible products. Right? So all the STs I can form as possible products. If T actually has only one guy in it, I'm not going to put the brackets in, and I'm just going to write ST. Right? Remember, matrix multiplication is not generally commutative, so ST is not generally TS, so the order is important, but we're taking all the products in the given order. It's easy to check that our 8-element group has 2 subgroups whose elements multiply to give the full group. And moreover, and importantly, that representation is unique. Each treatment assignment G in our 8-element set can be represented in exactly one way as first assign smoker control within the pairs, then assign a dose of smoking to the pairs. Why is the representation being unique important? Because if you give me G, I know how you did it, right? I know the H and the K. The actual study is just larger, has the same relationship. These are the factors in evidence factors, right? The factorization in evidence factors are this splitting apart of the treatment assignment. Actually, what we need is widely available. So whenever we have a finite group and a subgroup, we're in business. Okay. So whenever the world has a symmetry and that symmetry has a subsymmetry, we have what we need to construct 2 evidence factors. How do we do that? We take so what do I mean by that? I mean that there's a unique representation of every group element as the product of an element in our subgroup and an element in some other set that I'm going to construct. How do we get that other set? That other set is a system of distinct representatives of the cosets of the subgroup. So that always exists. So whenever we have a group and a subgroup, we have what we need for evidence factors. So let's number the group elements. In our case, it would be from 1 to 8 because we have 8 permutation matrices, right? We put them into a set. What's a probability distribution on our 8-element set? It's a vector of dimension 8, has 8 coordinates, where the coordinates are non-negative and they sum to 1, giving the probability of the different treatment assignments. What we've been calling a completely randomized experiment is simply we pick one of those 8 assignments with equal probability, 1/8, and we've also been considering sets of treatment assignments, which for observational studies where the probabilities might change from one element to another. All this resembles what we did before, right, except we're now talking about the joint behavior of the two factors rather than smoker control on the left and dose assignments on the right. Now we're talking about making both decisions. So we need to have the concept of a marginal distribution and a conditional distribution, and all this is going to be very familiar. We know that every element, every treatment assignment breaks apart into a factor of 2 matrices, right, in a unique way. What's the marginal distribution of K, the marginal distribution of smoker control? Well, go back to first lecture, Stat 1, right? It's obtained by summing the joint distribution over one of its variables, right? So if I have several mutually exclusive events and I want the probability that any of them occurs, I add up those probabilities. Lecture 1, Stat 1, that's the way you get a marginal distribution from a joint distribution. We also need the notion of a conditional distribution, the conditional distribution of dose assignments given smoker control assignments. But that's the second lecture in Stat 1, right? How do I get a conditional distribution from the joint distribution? I go back to the first lecture and I get the marginal distribution. I divide the joint distribution by the marginal distribution and I get the conditional distribution. So this is all discrete probability on finite sets, so there's nothing very difficult here. I really want to go the other way. Right. I have the set of marginal distributions, right, for smoker control from one sensitivity analysis. I have the set of conditional distributions of the dose assignments from the crosscut analysis. I want to put them together to get the joint distributions, right? So I already did the sensitivity analysis for smoker control, and that had a set P gamma of distributions, of marginal distributions. I already did the crosscut analysis using the conditional distributions of dose assignments giving smoker control, and they were in a set P prime. I want to build the set of joint distributions that are compatible with those sensitivity analyses with no added assumptions, right? I don't want to add any new assumptions at this stage. I especially do not want to add the assumption that H and K are independent of each other, because that would be crazy, right? The thought that the person most inclined to smoke is unrelated to the person who's most inclined to smoke a lot, that seems very implausible. Maybe the same things are inducing smoking and smoking a lot. So I don't want to add any assumptions like that at this stage. So let's think about building the joint distributions. Let's start with the simplest example, which turns out to be an immensely misleading example. It's an obvious example. It's an important example. It's a correct example, but it's a very misleading one. How would you get started? You'd say, well, let's take the simplest case. I'm talking about 2 sets of distributions. Why don't I just put one distribution in the first set and one distribution in the second set and figure out what are the compatible joint distributions. So we get a marginal distribution P of smoker control. I only have one choice, and I get a conditional distribution P prime from P prime, and from that I get the distribution of my product. Right? There's this immense urge to take those 2 distributions and do what? To multiply. And this sounds like the third lecture in Stat 1, right? If I have a marginal distribution and a conditional distribution, what do I do to make the joint distribution? I multiply them, right? But this is the third lesson in Stat 1 as heard by someone who wasn't paying attention. What's wrong with this? If I start with the premise that the set of conditional distributions has only one distribution in it, what have I done? I've done what I didn't want to do. I have said that no matter how the conditioning event comes out, the conditional distribution is always p prime. And how does that occur? Well, if they're independent. Right? So the very structure of having only one marginal distribution and one conditional distribution is imposed on the problem independence. And that's precisely the assumption we didn't want to make. So I've said this a couple of times. So you don't build the set of joint distributions by grabbing a marginal distribution and grabbing a conditional distribution and multiplying them. That adds the unwanted assumption that the two pieces are independent. There is, however, a new but obvious construction of all the joint distributions. I call it new because I haven't seen it before, but it's so obvious it must have been used a gazillion times before. How do I get all the joint distributions compatible with a certain set of marginal distributions and a certain set of conditional distributions? Well, let's build one and then we'll build them all. How would we build one joint distribution? I would pick a marginal distribution for smoker control. Then for each realization of who smokes and who doesn't, I would pick a possibly different conditional distribution from p prime. Right? And then I would multiply those out in all ways and get the joint distribution. One joint distribution. The knit product is simply saying, I liked what you did in step 2. Do it in all possible ways. Dump all of the resulting distributions in the set p double prime. Okay. Let's just understand how different these two answers are. Let's suppose my sets always have either one distribution or infinitely many in them. But let's suppose p had 2 distributions in it, p prime had 3 distributions, and the set of possible conditioning events has 4 elements, as in our example with smoker control. The mistaken answer grabs somebody from p and somebody from p prime. I can do that in 6 ways. It creates 6 joint distributions, but they're all independent. H and k are independent. The knit product says grab a marginal distribution from p. There's 2 ways to do that. For each realization of smoker control, of which there are 4, grab a conditional distribution from p prime. So there's 3 ways to do that for each value of the conditioning event. So there's 2 times 3 to the 4th ways to create the joint distributions, or 162 distributions in the knit product. So the knit product is way bigger than the mistaken answer we got. The mistaken answer comes out of randomization. Right? If I had randomized both factors, right, there would only be one distribution in each factor, and they would be independent. So it's an important example, and it shows up a lot, but nonetheless it's adding a powerful assumption which is only really justified in randomized experiments. There's one assumption about the test statistic for the first factor. The first test statistic has to be H invariant. What does that mean? It means that our test statistic is unchanged by the action of the H permutation. In particular, the signed rank statistic didn't care at all about the dose assignments because it ignored them, so it's invariant to the dose assignments, comes up with the same values, so it qualifies. It cared about the box plot, not about the scatter plot. Right? So that's the assumption about the first test statistic. And if we had such a test statistic, we could easily use the marginal distribution to get the sensitivity analysis as we did before. The second test statistic can be anything at all. I picked the cross-cut statistic for reasons I haven't fully explained. So we did a conditional analysis using the cross-cut statistic, conditioning on who smoked. We were looking at the relationship with doses. We got a sensitivity bound for the cross-cut analysis, and we did that previously. So where are we? We have this structure where treatment assignments factor into 2 pieces. First you assign smoker control, then you assign doses to pairs. One of our statistics doesn't care about the assignment of doses. We do the two hypothesis tests, one using the marginal test, the Wilcoxon test, the other using the conditional test, doses with pair differences conditioning on who's a smoker. We get two p-value bounds on the true p-values. This is that same claim stated a little more carefully now. If the null hypothesis of no treatment effect is true, if our marginal distributions of smoker control are one of the distributions in the first sensitivity analysis, if the conditional distribution of dose assignments given smoker control is one of the conditional distributions in P prime, then for every, when we look at all the joint distributions in the knit product, the upper bound on pair of upper bounds on the p-values is stochastically larger than the uniform distribution on the unit square. So no matter what true joint distribution there is, this pair of upper bounds on the p-values is stochastically larger than the uniform distribution, so we can act like it's two p-values from independent studies. So that's where we started from. We already did that analysis. Let me just indicate very briefly the idea of the proof. So the proof starts by saying, let's look at the knit product, all the possible joint distributions compatible with the two starting sensitivity analyses assumptions. It then says, first, that the answer I got by doing the marginal analysis for Wilcoxon statistic, the smoker control analysis, is identical to the answer I would have gotten had I worked with the worst distribution in the knit product. It didn't matter that I worked with the marginal distributions. Had I found the upper bound from the joint distributions, I would have gotten the same p-value. The second claim says I got the p-value for the crosscut statistic by looking at the conditional distributions, ignoring how smoker control was assigned. But had I taken that sensitivity analysis and computed it from the joint distributions in the knit product, I would have gotten exactly the same p-value, the same upper bound on the p-value. And then there's an easy standard kind of result which says if I do a valid marginal test and I do a valid conditional test, they combine to produce a pair of p-values that are stochastically larger than the uniform distribution on the unit square. And at the price of some additional notation, you can have more than two factors. There's nothing here special about two factors. Two factors is just the notationally tidiest case. So I want to try to reanalyze that example a little bit, but with a different group of permutations. So I have two goals in mind. One goal is to make it clear that what's going on has nothing to do with the particular groups we were talking about before, and I'll do that a couple of times. And I also want to look at what happens when we do a slightly different analysis, which I think is a more plausible analysis than the one we just did. Remember, the pairs were matched for age and sex. So we're always comparing a smoker and a control who are the same age and sex. But we were permuting the doses, the amount smoked, across pairs. So we're permuting them across people of different ages and sex. Within pairs, they're the same, but as we permute them across pairs, they're different. Actually, what's true is that the heaviest smokers tend to be young men. Women generally smoke less than men, and men tend to smoke less as they get older, and the health effects of smoking start to become apparent. So they're trying to quit, and it's hard, and they're continuing to smoke, but they're smoking less than they were before. So maybe it doesn't make sense to permute the amount smoked over all these different people. Maybe we should stratify the pairs by age and gender. So there are now 4 strata defined by age and by gender, and we're going to permute doses of smoking only within strata. So we're only going to permute doses among men who are young, or men who are old, or women who are young, or whatever. So the group is a little smaller than it was before, right? It's no longer got 441 factorial permutation matrices. It's got a smaller number. This is what the picture looks like for them, right? We now have 4 strata. We have 4 crosscut plots. You notice some of the odds ratios are a lot bigger than they were before. The odds ratio for young women is now 16, and the overall odds ratio was only about 3. Of course, the data is getting thin as we stretch it out over many strata. So we now have a 2 by 2 by 4 table of crosscut analyses, right? We used to have a 2 by 2 table, now we have a 2 by 2 by 4 for the 4 strata. I'll remind you that the Wilcoxon analysis became sensitive to bias at gamma equal to 2.75, was just about to become insignificant, and the crosscut analysis was insensitive to 1.6, but it was petering out at that point. And together they were insensitive to 2.9 and 2, larger values of both sensitivity parameters. How does that compare to our new analysis, which is adjusting for the 4 strata? So the Wilcoxon analysis is unchanged, right? But the stratified crosscut analysis, based on the 2 by 2 by 4 table, is somewhat less sensitive to bias. So a gamma prime of 2 would have explained our unstratified analysis, but it would not explain the stratified analysis where we restrict the permutations of doses to similar people. However, at some point, there's always a bias that will explain any causal effect. That's why association does not imply causation. Gamma equal to 2.25, both of these bounds for the stratified and unstratified crosscut statistic are now above 0.05. What if we combine the stratified analysis with the Wilcoxon statistic? Well, you notice that the resulting statistic is insensitive to even larger biases. So this is the combined analysis. Wilcoxon at gamma equal to 3, crosscut at gamma equal to 2.25. The combined analysis is insensitive to quite a bit larger bias than either statistic could have tolerated on its own. Again, 2 things are being illustrated here, right? One is a different analysis, maybe a more reasonable one. Second, more importantly for the current talk, I've changed the group, but the same theorem applies, right? And that'll happen in a variety of ways. There are lots of structures that give 2 evidence factors. We looked at pairs with treatments assigned within and between pairs. That's a simple structure. What other structures do this? Unsurprisingly, the blocks could be of equal size, but they could have more than 2 people in them. So we could be permuting some treatments among blocks and some treatments within blocks, like in experimental design. The blocks don't have to be as tidy as they would be in a balanced experiment. For example, we could have some pairs and some triples. There might be a deficit of treated people at certain values, so we wind up with more controls available, so we have pairs and triples. Then the permutations would be restricted to blocks of the same size, but we'd still have 2 evidence factors. We permute things among pairs and among triples. It doesn't have to be pairs and triples. They could be of varying sizes. It could be a full match, which matches everybody in the study, but uses structures that are varying in how many treated and controlled people there are in each match set. A very different kind of a structure has a treated group and a control group, but the treated group really subdivides into 2 variants of the treatment, where one was thought to be more potent than the other. And we'll look at one of those in a moment. An important feature of this is that these activities are really about kind of taking group products, and so they can be compounded. So you can do one of these things on top of another thing on top of another thing. You have a treated group and a control group, where the treated group subdivides into 2 variants of treatment, and that could be going on between blocks, and there could be further treatments that are being applied to the whole blocks and varied among the blocks. You can do these things one on top of one another to produce lots of different variants of evidence factors. I want to give another example, simplest possible example, but it takes a moment or 2 to realize that the theorem we talked about is actually relevant to it. So this is essentially a one-way analysis of variance with 3 groups, but it could be also a 2 by 3 contingency table with 3 groups, or a variety of other similar structures. This will also have 2 evidence factors. It's from a study of cancer chemotherapies, anti-neoplastic drugs. So these drugs are very biologically active, but not only may they damage cancer cells, which they're intended to do, but they may damage healthy cells. In particular, they may damage healthy cells of people who don't have cancer, but who are preparing the chemotherapies for administration to patients. So this was a study that appeared in Mutagenesis a number of years ago, which compared doctors and nurses who prepared chemotherapies to office workers and students who had no exposure to chemotherapies. So the first factor is exposed versus control in this study. Turns out that some of the workers wore latex gloves as protection. That was about half the worker group. But some of them were also protected by a ventilated cabinet with vertical airflow. So they would stick their hands into this cabinet. The cabinet was open, but it had a kind of glass or plexiglass screen, and there was vertical airflow carrying the fumes from the drug preparation up and away. Right? So it's possible that such a thing reduces the harm from exposure to cancer chemotherapies, or it's possible that since the thing is open, it really doesn't really matter too much whether there's this vertical airflow or not. So the second factor is comparing 20 workers to with gloves to 19 workers who also had a vertical safety hood. The outcome is a standard measure used in genetic toxicology called the comet assay. So it actually refers to the shape of a comet's tail. So what's done in the comet assay is a cell has its cell membrane removed, and its DNA is removed from its nucleus, and it's placed in an electric field. DNA is a big structure, so if the electric field pulls on the DNA is so big it barely moves, and intact pieces of DNA are left here unmoved by the electric field. If a piece of DNA has been broken, it's much smaller, and the electric field pulls it to the right, and that's producing this appearance of a comet and its tail. And the tail moment is the magnitude of this tail, and it's taken as a standard measure of DNA damage used in genetic toxicology. So we're looking at the tail moment for our three groups, and this is the way it's coming out. The control group is down here. They're the students and office workers. These are the workers who are protected by the ventilated hood, and these are the people who are only protected by the gloves. So it's coming out the way you might have thought if the hood was of some benefit but was not totally protective. This comparison here is our first factor. It's control versus exposed, so it's about 20 versus 39 people. This is the second factor. It's looking just at the exposed people. It's comparing those who worked with gloves to those who worked with hood. Obviously, this box plot is related to these box plots because, after all, if you remove the boxes, put the points in place, projected the points to the left, you would get this box plot as the entire exposed group. Either of these comparisons could be biased, right? Doctors and nurses are exposed to cancer chemotherapies, but they're exposed to everything that's going on in hospitals. And maybe it's something else, some other toxin in the hospital that's separating the two groups and creating DNA damage for the exposed group. So there could be bias in the first factor. There could be bias in the second factor. If you work at a hospital where they care enough about you to provide a ventilated hood, maybe they're doing other things to protect you from toxins, and maybe it's that protection from other toxins that's really mattering, not just or not even the protection from cancer chemotherapies. However, the two factors feel like, if they're biased, they have to be two very different biases. After all, what separates workers and controls is very different from what separates one worker group from another, because, after all, everybody in this box plot is in the hospital and is either a doctor or a nurse. And so they're all more similar on some of the things that might have been dissimilar for the controls. So it would take two biases to produce this, and they'd have to be different in nature. The plan is to do what? Is to use Wilcoxon's rank sum statistic to make this comparison, to do Wilcoxon's rank sum statistic to do this comparison, and then to pretend that the two studies came from unrelated research teams working with different data sets which have nothing to do with one another. Does that make sense? They're obviously not actually unrelated because the exposed group is simply the merger of the hood and gloves group. Nonetheless, Dwaz and Martin have shown that those two Wilcoxon tests would be independent in a randomized experiment without ties under Fisher's null hypothesis. So exactly independent in that case. And they're discussing a number of things. Martin in particular is talking about more complex contrasts than just the one we just looked at. We want to get away from randomization and talk about sensitivity analyses because we're worried that there may be bias, and that's our main interest in these two factors. We don't mind rank tests, but we don't want to have to use rank tests if we wanted to use something else. And we feel a little bit like, why do we have to worry about ties, right? And in fact, we can do all of those things. So the version we'll be talking about, that theorem we talked about, won't care about the ties, lets you use tests other than rank tests, and moves you into sensitivity analyses and not just randomized analyses. So this is the sensitivity analysis, the joint and the separate sensitivity analyses for our two factors in that study. So what are we seeing in this sensitivity analysis? The worker control analysis is enormously insensitive to bias. It would take a gamma bigger than 50 to produce the pair of box plots in that first factor. The hood versus no hood analysis is also very insensitive to bias, not like 50, but still very insensitive to bias. It would take a bias substantially bigger than gamma prime equal to 3 to produce the second factor. But if you put together those two analyses, right, the combined analysis is highly insensitive at the point where these are getting close to 0.05. If you went out to gamma prime equal to 4, much bigger than 3, and gamma equal to 125, much bigger than 50, the combined analysis is insensitive to a bias of that magnitude. So once again, we're seeing that the combined analysis is insensitive to larger biases than its components. You also notice that if we demarcate the evidence and say, what evidence do we have if we throw away the hood analysis is completely biased, the combined analysis is still insensitive to a bias of gamma equal to 25 when there is infinite bias affecting the hood analysis. In much the same way, if there is infinite bias affecting the worker control analysis, the hood analysis still is insensitive to a bias of gamma equal to 2. So we have a lot of evidence from each factor that isn't dependent upon the other factor, and on top of that, the combined analysis is insensitive to larger biases than either factor was on its own. How does this fit with the basic structure? So we're going to divide n individuals into 3 treatment groups of size m, m prime, and n minus m prime. There are n choose m times n minus m choose m prime distinct ways to do this. Right? So a permutation matrix is one of the matrices that does this division. In our example, we have 59 people, so we're going to pick 20 people for control. Having done that, we're going to pick 19 people, leave the controls alone, and pick 19 of the remainder to be given a ventilating hood or cabinet. So the basic structure we need is that each of our treatment assignments is the product of 2 decisions, 2 permutation matrices, and we're going to build such a representation. We need to find 2 sets of permutation matrices which together give us all of the treatment assignments in a unique way. Not surprisingly, the set K is going to pick our 20 controls. The set H is going to say, leave the 20 controls alone, let me now pick the 19 people who are going to get the hood from among the remaining people. This leads us to what are known as pick and sub-pick matrices, two special types of permutation matrices. So I'm just going to talk over this slide. You can read it if you like. A pick matrix is essentially going to pick a few people for one group and put the rest in the other. And it's going to leave people otherwise in their original order. So we're only going to represent each treatment assignment in one way. So if I zap the 1, 2, 3, 4, 5 with this particular pick matrix, it's picking persons 2 and 4 for the first treatment group of size 2 and putting the others in the second treatment group and keeping them in their original order, 2 before 4, 1 before 3, before 5. So this is saying what a pick matrix is. What's a sub-pick matrix? Sub-pick matrix says fix the people you picked, right? And now pick some more. It's got an identity matrix in the upper corner, and it's got a smaller pick matrix in the bottom right-hand corner. This is a sub-pick matrix. It has an identity matrix in the upper corner, leaving the people we picked initially alone, and it's going to pick some more people. It's easy to check that we've got the number of pick and sub-pick matrices are just what we need to produce our complete representation of all of the treatment assignments. In particular, you take these people 1 through 5, you hit them with a pick matrix, you get this treatment assignment to the first two to the treatment group and control group, and then you hit it with the sub-pick matrix, and it subdivides the treated group into two parts. And obviously you can do this more than once, right? You can have sub-picks of sub-picks, and you can sub-pick from a group you've already picked, and all kinds of variations on a theme. What does this have to do with groups of permutation matrices? The group in this example is the group we don't care about. Right? And sometimes that's always true. Right? A group is about a symmetry, and a symmetry is a change that we're indifferent to. What is the symmetry that statisticians are indifferent to in a one-way design? We don't care how the people are ordered within their respective treatment groups. Right? Among the people who are assigned to the first group, we don't care how they're ordered. Among the people assigned to the second treatment group, we don't care how they're ordered. So there's a permutation group that's rearranging people inside their treatment groups, and it's precisely that we find uninteresting in our test statistics. Ignore it. Our F-test or our Kruskal-Wallis test would ignore it. If you take the set of pick matrices and then multiply it by the set of sub-pick matrices and then multiply it by the permutations within groups, you get the full symmetric group, all the ways of permuting people. If you take this uninteresting matrix, which is permuting people within groups, and you multiply it just by our sub-pick matrices, you get another group of permutation matrices, which is fixing the division into control and treated, and is allocating each of those people and ordering, which is affecting who's getting the hood and who isn't getting the hood. H, our sub-pick matrices, are a system of distinct representatives of the right cosets of W in the group WH. HK is a system of distinct representatives of the right cosets of W in the symmetric group. So once again, we're getting the structure we need, this unique representation, by taking a subgroup and looking at the distinct representatives of their cosets. Our first test statistic, the Wilcoxon statistic for the first factor, was invariant to the second decision. We have everything we need to apply the theorem. I'm just going to say a couple words about the algorithmic aspects of design. So it's common to form match pairs by in a treatment control design, and to set that up as an optimization problem. So you might form, let's say, 5,000 treatment control pairs, such that the pairs are never far apart on the propensity score, a constraint, such that you minimize an optimization. You minimize the total within pair Mahalanobis distance on key covariates, while you're perfectly balancing the marginal distribution of a nominal variable with 1,000 categories. So it might be ICD-10 codes for something. That problem can be solved fairly quickly in polynomial time. So you could do it on your laptop with 5,000 match pairs, and you wouldn't have time to get coffee. Perhaps surprisingly, it's much harder to create complete blocks with 3 treatments. That's a harder problem. Um, just a comment about algorithm theorem, right? The size of a problem is like the number of people who we want to match, right? And we're imagining problems of different sizes. We say that a problem is polynomial time if there exists an algorithm which can solve it in time that's bounded by a polynomial. So there's some power of n such that we can solve the worst, most difficult problem in n to the omega steps. So you can sort n numbers in O(n) log n or O(n) squared time. The matching problem, the reason why we can solve it on a laptop, it's an O(n) cubed problem. It's not that difficult. There is, however, a category of problems for which no polynomial time solution is known. They're reducible to one another, so if you solve one, you've solved them all, and nobody can solve any of them in polynomial time. And it's believed that they don't have a polynomial time solution. They're called NP-hard problems. Turns out this problem of forming matched triples is in this category of much harder problems. So we're not going to be able to solve it exactly. You could do a heuristic, something which just sounds reasonable. It turns out that's a terrible thing to do in matching. The heuristic solutions to matching problems are much, much worse than the optimization solution. An alternative to just kind of making something up that runs in polynomial time is an approximation algorithm. So this says I can't solve the NP-hard problem, but maybe I can solve closely, right? So an approximation algorithm comes with a promise that it produces a solution that is at most lambda times the optimum. The heuristic that's described here can be infinitely worse than the optimum, but this is coming with a promise that it's not much worse than the optimum. If lambda were 5, then the minimum you found is at most 5 times the true minimum. And it usually is the case that it's some weird construction that produces the bound, so you don't see 5 very often. Bikram and Dylan and I proposed a technique for doing this with 3 groups or more than 3 groups. Could be matched triples, could be 1 to 2 to 2, could be several treatments with varying numbers. It's building on some ideas of Kramer and Spieksma. I'm going to describe it very briefly due to time, but suffice it to say this is a 2 approximation algorithm. It gives a solution in polynomial time that is, in the absolute worst case, at worst twice the true minimum. And how does it work? It uses a distance that satisfies the triangle inequality, and it first pairs 2 groups, A and B. It takes the pairs that came out of A and B, and it pairs them with group C, and both of those steps involved at most n cubed steps. The bad news is you might regret some of your AB pairs when you look at group C. The good news is you can't regret it very much. The triangle inequality and some careful tinkering with the bookkeeping shows that you can't regret your AB choices very much for a distance that satisfies the triangle inequality. The worst case, you'd regret it by doubling your minimum distance. Bikram's approxmatch algorithm in R will do this. So let me close the discussion of approximation algorithms here and summarize. In observational studies, both biases and treatment effects can replicate across independent studies. So effective replication is not doing the study over again. It's not repetition. If you can't remove an unmeasured bias, maybe you can disrupt it and replace it by a different one to see if the same treatment effect reappears despite changing the biases. Viewed in this way, a single observational study can replicate itself, performing several independent comparisons, potentially affected by different biases. The joint analysis of 2 evidence factors may provide measurably stronger evidence of cause and effect, evidence that we are looking at a causal effect and not at an unobserved bias, than either of its component analyses does on its own, and there can be more than 2 evidence factors. Evidence factors were built from a finite group of permutation matrices that assigned treatments to people. and a system of distinct representatives of the cosets of that group. From this structure, two separate sensitivity analyses may be combined using meta-analytic techniques as if they were independent, even though the joint distribution of the in the knit product allow for very strong dependence among the two treatment decisions. So let me close there. I'd be delighted at this point to have your comments or questions.